Hi students, in the linear transformation we will be seeing theorem 1. What is theorem 1? Let S and T be two let S and T be two linear transformations from U to V, where dimension of U equal to n. Let E1, E2 and so on to En be a basis of U. Suppose S of EI equal to T of EI for I equal to 1, 2 and so on to n, then S of U equal to T of U for all U belongs to U. Okay. So what is given here is S and T are two linear transformation from U to V. Okay, S and T is because it is linear transformation, its property holds, and moreover dimension of U equal to n, and basis is also given for U, and we have suppose S of EI equal to Ti also is given, and we have to prove that S of U equal to T of U. So what we will do is, let U, we will take one element U in U, let U belongs to U, since E1, E2 and so on to En is a basis of U. U can be uniquely written as so U is nothing but is an element of U, and basis is also given. Because basis is given, we can write a linear combination. U can be any element in U can be written as linear combination of the basis. So using the property, we can find alpha i's, that is scalars, such that U can be written as alpha 1 U E1 plus alpha 2 E2 plus and so on plus alpha n En, where alpha i's are scalars. Fine. Now we will find now S of U. What is S of U? S of alpha 1 E1 plus alpha 2 E2 plus and so on plus alpha n En. And it is given that S is a linear transformation. Therefore, it can be written as alpha 1 S of E1 plus alpha 2 S of E2 plus and so on plus alpha n S of En. Right? But it is given that S of EI equal to T of EI for every I. Therefore, S of EI can be replaced by T of EI. That is, S of E1 can be written as T of E1, alpha 2, T of E2, plus and so on, plus alpha n, T of En. So this can, again T is a linear transformation. Therefore, we can write this one can be written as T times alpha 1 E1 plus alpha 2 E2 plus and so on plus alpha n En, because T is also a linear transformation. Previously here we used S is a linear transformation in this step, and then and here we used the step that S of EI equal to T of EI, which is given in the theorem, and then in this step we use that T is a linear transformation. Using these properties we are able to prove the theorem, which is equal to alpha 1 E1 plus alpha 2 E2, all these are nothing but our U. So ultimately it is equal to T of U. So what we have proved is that S of U equal to T of U. we have taken u at random, therefore it is true for every u. So theorem 1 is proved. Now we go to theorem 2. What is theorem 2? Let V be a real vector space. It is given that V is a vector space and T from R to V, okay, be a linear transformation. It is given that T from R to V is a linear transformation. Then there exists V in V such that T of alpha equal to alpha V, T of alpha equal to alpha V for every alpha belongs to R. So, sorry, it is proof. What are the information given here? We'll see. The first information given here is V is the real vector space. Okay, so vector space properties, there are 10 properties. V is having all the 10 properties, it satisfies. Moreover, T from R to V is a linear transformation. These two information is given. Then we have to prove that there exists V in V such that T of alpha equal to alpha into V for every alpha belongs to R. So we will take, in order to prove that, we will, what is the basis of R? Basis of R is singleton set 1. Okay, every element in R can be written as linear combination of 1. For example, root 2 can be written as root 2 into 1, root 3 can be written as root 3 into 1. So every element in R can be written as linear combination of 1. Therefore, 1 is the basis, singleton set 1 is the basis of R. So a basis for R is singleton set 1. Let T of 1 equal to V belongs to V. Okay, T from R to V is a linear transformation, it is given. Therefore, T of 1 can be written as V, right? So, for some V in V, then for any alpha belongs to R, what is T of alpha? T of alpha can be written as T of alpha into 1, right? And it is given that T is a linear transformation. Therefore, we can write alpha times T of 1. Okay, what is T of 1? T of 1 is V. So, T of alpha equal to alpha into V, right? That is what we are supposed to prove for every alpha belongs to R. So, now we go to the theorem 3. Okay, what is theorem 3? Theorem 3 states that let E1, E2 and so on to En be a basis of U, and let V1, V2 and so on to Vn be any n vectors in V, right? So it is given that E1, E2 and so on to En is a basis of U, and V1, V2 and so on to Vn be any vectors in V. Then there exists one and only one linear transformation T from U to V such that T of Ei equal to Vi, I equal to 1 to and so on to n. What is given here, basis of U is given and n vectors of V is given. There exists only one, we have to prove there exists only one transformation, right? T from U to V such that T of Ei equal to Vi for I equal to 1 to n. We will take some element U belongs to U. Then what is given? U, for U the basis is E1, E2 and so on to En. So any element in U can be written as linear combination of E1, E2 and so on to En. Then U can be uniquely written as U equal to alpha 1 E1 plus alpha 2 E2 plus and so on plus alpha n En for some alphas where alphas are scalars, right? Now we are going to define T of U. Okay, T of U is alpha 1 B1 plus alpha 2 B2 plus and so on plus alpha n Bn. Why we are defining T of U? Because we have to prove that T of Ei such that T of Ei equal to Vi, right? So where T is a linear transformation. It is given that T is a linear transformation from U to V. So we can define T of U in this manner. Then T defines, T is linear transformation we have to prove. Oh, there exists one and only linear transformation from T from U to V. That is what we are supposed to prove. We are now assuming that T of U equal to alpha 1 V1 plus alpha 2 V2 and so on to alpha n Vn. Then T defines a mapping. Only a mapping, we don't know about the linear mapping and all because that is what we are supposed to prove. T defines a mapping from U to V such that T of Ei equal to Vi for every I equal to 1, 2 and so on to n. So then this T is mapping, some mapping such that T of Ei equal to Vi. Okay, because we are taking U from U to V, no? Ei is an element of U, right? Because it is given that E1, E2 and so on to En is the basis of U. So naturally Ei belongs to U. Therefore we can define that T of Ei equal to Vi because T is a map from U to V. Let us now show that T is a, just we have defined T is a mapping, that's it. Now we are going to show that T is a linear map. So in order to show T is a linear map, we will take A and B, B scalar. We will take two scalars A and B. And U dash belongs to U. Then there exists alpha 1, alpha 2 and so on to alpha n, beta 1, beta 2 and so on to beta n. Because U and U dash are two elements of U, therefore U and U dash can be written as linear combination of E1, E2 and so on to En. Both can be written as linear combination. That's why we took n